Okay, 1.2, we're just focusing in on graphs of all types of functions. It's not going to be super intense. We're not going to be graphing. We're going to look at a graph, and then we're just going to identify key features. Don't write this stuff down. It's too much to write down. So it's all stuff we know. They're going to ask you to identify, what does the graph look like? Is it just a set of points? Is it a line? Is it a curvy graph? What are the x-intercepts? Where's the max and min values? Where's the local max and mins? Where's the symmetry, if any? Asymptotes, domain range, intersection points. It's pretty basic. You're just going to look with your eyeballs. So look at this right here. We're going to see all types of shapes. What shape is this? If I asked you on the test, what shape is this? You'd say a line. We all know what a line looks like. Yes, a straight line. Yes or no? Okay, so don't overcomplicate this, my friends. If I ask you the shape of this, it's a line. Okay, now from here, let's practice from last time, the domain and range. They'll ask that again. What's the domain? Let's do interval notation. Where's it going from left to right? Negative infinity to infinity. Very good. Infinity always gets a parenthesis. All right, range down to up. Negative infinity to infinity. Very good. All right, what's the shape here? It's a parabola. If they said to you, is it curvy or straight? You'd say curvy, right? Obviously. Okay, cool. Domain on this is left and right. What's the domain from left to right? Negative infinity to infinity. What's the range? Yep, -2 to infinity. Details matter. Infinity gets a parenthesis, and what does our number get here? A bracket. Okay, good. That's what we learned last time. All right, so once again, right here, if they ask you the domain here, you would say, well, it's a straight line. My domain is from, I'm not going to write it down. I'm just going to verbalize it. Is that okay? Yeah. We see the domain is from 1 to 6. You're right, 1 to 6. Then our range is from 1 to 6. Now, because these are closed circles, you would do brackets on that. Okay, so it was 1 to 6. I said I wasn't going to write it down. I did anyways. Now, just a friendly reminder, if there's just a set of x, y points not connected, you actually always write out the domain separately. So you would do the little squiggle, and then you just write the x values. The x values are -2. The next x value is 1. The next x value is 2. The next x value is 3. The next x value is 6. True? And then once again, if it's just x, y points not connected, we don't do an interval, we just write them out. We'd say the range is -2, and then it's at 1, then it's at 2, 3, then it's at 6. This just happens to have the same domain and range. That doesn't happen very often. Okay, awesome. All right, I think we get the picture here. I just wanted to remind you, if you have an open circle, that means it's not including. So let's state the domain and range just to be sure. What's the domain from left to right? Let's do interval notation. Left to right. -1 to 1. Now, once again, details matter. You're right. At 1, we get a bracket. Sorry, when I said at 1, what I really meant was at -1. Yes, everybody, at -1, it gets a bracket because it's a closed circle. At 1, it's an open circle, so we do a parenthesis. Our range is, well, actually, they didn't ask the range on this one. They just asked the domain. So, pretty basic here. All right, we get the picture here. All right, now, they're going to ask you if your graph is continuous or non-continuous. Don't overcomplicate it. In your notes, you could write continuous and non-continuous because they will ask that. A continuous graph has no gaps, holes, or breaks. It just continues from left to right all the way through. Basically, a continuous graph will have a domain of -infinity to infinity. And once again, there would be no holes, gaps, or breaks. So very basic. Let's just keep it straightforward. So if you look at this graph, it would be considered a continuous graph. Do you guys see how it continues from left to right, never breaks, gaps, and there's no holes? This would be considered non-continuous because notice right here, once the graph was going, it then picked up its pencil, jumped to the other side, and then continued. That created a gap right here. Sorry, I just wanted to draw it in. It created a gap in the graph. Do you guys see it? So non-continuous. That's really all we're going for. So let's look at this one. Is this considered a continuous or non-continuous graph? It's non-continuous. So pretty easy stuff. Now they're going to ask you to identify x-intercepts and y-intercepts. They do want you to write your x and y intercepts as x, y points. So we'll do that with practice. Let's look at this one. Let's answer Our x-intercepts how they want us to answer it, and our y-intercepts. So once again, our x-intercepts are happening where it crosses the x-axis or bounces at the x-axis. Bounces and crosses at the x-axis are intercepts. So we write the following answer as such. Our x-intercepts are over 1 up 0. Do you guys agree? The next x-intercept is, you tell me, 3, 0. The y-intercept is where it crosses the y-axis, and once again, they want it as an xy point. That's over 0, but up 3 units. So don't overcomplicate it. All right, awesome. The next thing they want you to talk about possibly is turning points. So they might say to you, how many turning points do you see? They might say, list the turning points. Turning points are when the graph changes direction. So changes from increasing to decreasing or decreasing to increasing. So when you guys look at this, where is the turning point located? At what XY point? Where does it change direction? Yep, right here. Isn't this where it changes from decreasing and then all of a sudden it starts increasing after that? So you're right. The turning point here is over to -1. Now, turning points are going to be what are considered local max and local min on our graph. So now you're just labeling the turning point. Is it a maximum or minimum? Now, we have to use the word local. There can be more than one local max and min on a graph. I'll show you an example where that happens. Right now, there's only one. Is there a local max? Here. Now, local means in the middle of the graph. Is there a top of the hill? If you look at this, is there a highest point on this graph? Locally. In the middle? No. So you would say there is no local max. None. But is there a local min? Look in the middle of the graph. Is there a bottom of the hill? Right here. Isn't this locally a minimum value? Yes? So you'd say my local min, I believe, if I'm not mistaken, that how they want you to type it into your computer is as an XY point for local max and min. So I believe we would say it's at 2, -1. Now they're going to use the word global. So now we're going to talk about global max or mins. So global is exactly what it sounds like. Overall, on the entire graph, is there a maximum stopping point? So everybody look, on this graph, is there an overall stopping point on the maximum? Doesn't it go to positive infinity? So our max is going to infinity. Infinity is not a number, so you can't write that as an answer. So you would say there is no global max, none. But there is a global min. That means overall on the entire graph, what is the lowest point possible? What would you say? Lowest point possible. Min is low. Yep, 2, -1. Isn't that the lowest point down?
I have a question.
Yes.
So can you have multiple, I'm just trying to make sure I understand.
Yeah.
Can you have multiple local max points and
Yep.
multiple local min points, but you can only have one global max?
I'm really glad you said that. Exactly. So she makes a very good point. You can have more than one local max and min because it's just like saying, what are the turning points? Turning points are local max and mins. When you go to global, you do overall. And so there's only one answer. So on this, the global min, it's interesting. Honestly, on the test, I won't care if you write it as an XY point, but I believe from my research, the computer wants you to type global max and min as just the Y value. So isn't the Y value -1, everyone? So we would say Y equals -1 is the global minimum. That's the furthest down point, is the Y value of -1.
Would the global max be just the x?
So no, global max is once again up and down, but it goes to infinity. And so if we wrote infinity, it's not that we're wrong. It's just like, that's, yeah, not exactly a number, right? It's a place. Awesome. So she makes a good point. Let's go look at an example where there's more than one turning point. So it's, what's annoying is I'm going to make the points, I'm going to make them a little more like, I'm skewing them because this isn't a very super straightforward graph unless I create points that are more straightforward. Okay, so let's start out with what they might ask. What are the x-intercepts? Write them as points. That means where it crosses or bounces. So what would be the first point right here? I think it's at -10, 0. True? I don't remember, but in the computer, they might want you to put this little union sign to get it right. On the test, I don't care. But on the computer, union just means also. Also, and then we do 0, 0. Isn't that also an x-intercept? Yes, because a bounce is also an intercept. Then we do y-intercepts. Our y-intercept is at, once again, 0, 0. Then they're going to ask for local. Oh, this only has one, but it's fine. Is there a local maximum? Top of a hill. Yes, everybody? So what's the local max at? We're going to say, for easy purposes, we're going to say it's right here and right here. So what would that be? -7 up 18. Local minimum, locally speaking. Where's a local min? Right here. True, everybody? So you'd say 0, 0. Now we're going to do global. That means overall. So global max. Is there an overall highest point here?
Yes.
What would it be? Overall, what's the highest point possible on this graph? Infinity. Yes, everybody. So that would be none, because infinity is not a number. Global min. Is there a lowest value, period, end of story here? Okay, so there is also no global minimum. It goes to negative infinity. So you would once again say none. Now, if they asked you the turning points, this is a turning point, this is a turning point. Okay. So, like right here's a better example. Let's just do the one thing that it's asking on these instructions. It says, identify the global maximum and minimum values of the function. I want to practice local max and local min. That means in the middle of the graph, is there a top of a hill and a bottom of a hill? Yes. So what would be the local maximum? Right here, yes, everybody? So I think with local max and mins, they want them written as XY points. But I would accept 4 as an answer. Isn't 4 the highest value, or the Y value? But I'm going to write mine as XY points. So over 0, up 4 is a local max. Is there 2 local mins? Yep, there is. There can be 2 local mins. So in this case, we would say -1.5 down 2. And also, union just means also 1.5 down 2-ish. Now, when they ask for global, you look over overall, global max. Where's the highest point here? Infinity, so none. Then global min, they write just the Y value. So where is it at? The lowest value, period, end of story. Y equals -2. Everybody see how that's working? What are your questions on this? Okay, cool. And those are also turning points. Very, very good. All right, so sometimes they're just going to say to you, what does this graph have symmetry over? So symmetry means it's perfectly symmetric over some axis. We're only going to do symmetries over axes today. So you could have symmetry over the x-axis. That means if you were to stamp, literally like put ink on this side and stamp it across. Do you guys see what I'm saying? It's the exact, that's the x-axis, right? I didn't mess that up. So that would be considered symmetry over the x-axis. Symmetry over the y-axis would be like if we had a graph like this, we would stamp it across the y-axis and it would look exactly symmetric. Do you guys get the picture? Then there's also symmetry over y equals x. Y equals x, remember, is a line. X to the first is a line. So y equals x is a line. Technically, just if you want to be technical, that's technically y equals x plus 0. That is the same thing as y equals x. So if you were going to graph that, the y-intercept would be at 0, 0, notice. And then our slope is 1, if you remember how lines work. So look at this slanted line. See how it's up 1 over 1, 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 up 1 over 1. You get the picture, yes? So then this is this nice slanted straight line. This is considered the y equals x axis. So look, if you stamp it across, fold it across that red line, would it match up? If I put ink right here, and we stamped it across the red line, would it end up right here? Yes, it would, my friends. Picture it like a piece of paper, stamping across. So this would be considered symmetry over the y equals x axis. So they ask you on the test, determine the line of symmetry. Where is it symmetric over? So you'd say the y-axis. Now I believe it says determine the line of symmetry. Now that I think about it, I didn't think about this last hour. They might want the actual equation of where it's symmetric. So where is it symmetric at y equals? Oh no, that's actually backwards in my mind. I did that wrong. I put y equals, but want to know why my brain went that's wrong? Isn't y changing on that line? Y is like a million different numbers, but x is what every time here? X is always at 0. So I don't know on the homework I would accept either on the test. Determine the line of symmetry. I think they just want the y-axis, but that is this equation, x equals 0. Alrighty then. I was just seeing if there's any others. All right, so also we're not getting into do you guys remember back in Sec 3, like how rational graphs have asymptotes, some graphs have asymptotes that are other types of graphs, and asymptotes can seem complicated, yes? We're not getting into the complications of asymptotes today. They just want you to know if you can look at a graph and decipher things. So we are first going to focus on asymptotes, and I'm going to have you write this down. They might ask you, what is the horizontal asymptote? So horizontal asymptote is to the far left and or the far right. We do not look in the middle of the graph. So I'm going to make a little note of that. Don't look in the middle. We look to the very far right and left. Basically, we look out towards infinity and negative infinity and see if on the horizon it's approaching some y value. So horizontal asymptotes are always written as y equals. So y equals, and it will be some number that it's approaching on the horizon. Now, vertical asymptotes are up and down. So horizontal will go like this. Vertical asymptotes are up and down, and we just look and see if there's a gap. It's going to be a gap in the graph, a break. So, and it's going to be x equals, oops, I wanted to do it in red. X equals some number that it's getting close to and then jumping over. Now, I mean, they talked about it in the textbook, but it doesn't really matter for the level we're at right now. But they do talk about how horizontal asymptotes can actually get crossed, where vertical asymptotes cannot, but they just say that, and they don't go into why in the book. So to me, it feels a little unimportant right now. If we needed to know why, it would come up. So that's besides the point. In the future, we do learn how to graph rationals, and I can teach it really well. So if you thought it was hard in Sec 3, I teach it better. So then you'll learn why horizontal can get crossed and why vertical can't. We're not getting into that today. So all it asks, follow the instruction, is here is a graph with a function with a vertical asymptote. What is the vertical asymptote? So they even told you, we just want you to identify the vertical asymptote here. So if you guys look, vertical is like this, true? So look up and down. Is there a value it's approaching? So look up and down. Do you guys see? Yes, so right there, I then just go like this. I use this trick. I then know that my line is really, really close to that, and I just go straight, straight, straight. Straight, straight, straight. So what would be the equation for this vertical asymptote? What does x equal right there for sure, every time? X equals -2 would be our answer. All right, with this one, they said right here has a horizontal asymptote. What is the horizontal asymptote? So you look to the negative infinity or positive infinity. So where is it approaching on the horizon out here? What value? Once again, go straight, straight across. -4. True, everybody? So then you would say y equals -4. So pretty easy. Like I said, for today's lesson, we're staying really basic with asymptotes. So once again, what if they gave you this graph on the test and seriously asked you, what is the horizontal asymptote? Here and here. We look on the horizon. Yes, outside, not the middle. It has nothing to do with the middle of the graph. What value is that? +3, right, everybody? And then same up here, yeah? 3. Yes, everyone. So the horizontal asymptote is it x or y equals? It's y equals 3. Isn't it crossing the y-axis right there? So y equals 3. Now let's do vertical. They've even listed them out for you. What are the vertical asymptotes at? X equals -1 and x equals 4. Okay, so that's as basic as we need to be with the 10-10 stuff with asymptotes today. Good, good, good. I think you get the picture with that. All right, now we find out in the future, sometimes it can be useful to put two graphs on the same graph and find their intersection point. Today, we're not getting into what the intersection point is. All they want you to do is, can you identify the intersection point? So you guys tell me. We have a line and a line. Can you guys identify the intersection point?
1, 3.
Yep, so 1, 3. It's that easy. That's how basic we're staying with today's graphs. What are your questions? Now look at this one. So once again, if they said to you, what are the intersection points? I already wrote them down for quickness purposes. The first intersection point is -3, -6. The next intersection point is over 2, -1. So notice on this one, there's a parabola and a line graph, and there's their intersection points. All right, so like I said, on the test, they really will ask, state the intersection points of the two functions. It's not a trick question. It is supposed to be easy. You would tell me, what is the first one? -3, -5. And then just to be proper on the computer, I think they make you do a union, and then 3, -5. True? All right, details matter there. All right, that's all we're getting at right now. Can you physically see with your eyeballs an intersection point? Easy, easy, easy. That's the end of 1.2. We literally went twice as fast as first period, so that's good, right? All right, then they took a 5-minute break. That was a bad idea. Wouldn't you rather just work on homework at the end?
Yes.
So we're not going to take a 5-minute break. Sorry, we're going to move on. So in your notes, let me stop this video and start a new one.